So I'm gonna introduce the Ricci flow and just say some old results and some newer results, and then I'm gonna at the end say something that what we did recently regarding the singularities. So the Ricci flow equation was introduced by Hamilton in the 80s, and it's the equation that you have on this slide, namely you start with the Riemannian metric G on a complete manifold, and then you evolve it by this equation where the ddt of G is -2 Ricci, where Rij is just the Ricci curvature of your metric on the manifold. And Hamilton actually introduced this flow in his work in the 80s in order to prove the Poincaré conjecture. So that was his goal. And we all know what it is, that every simply connected closed Riemann manifold is homomorphic to a three-sphere. And I'm going to say, in a little bit, what he actually did in this paper where he introduced the Ricci flow. But I will just say that in dimension 2, this equation gets even simpler because the Ricci curvature is just, you can write it in terms of the scalar curvature. And then it just becomes a scalar equation that you study in dimension 2. And due to the results of Hamilton and Chow, who considered the Ricci flow in 2 dimensions, they proved that, so after renormalization, so they do reparametrization of the flow to keep the volume of the manifold fixed. And they proved that then the flow exists for all times and exponentially converges to a round sphere, right? So no matter what the sign of the scalar curvature is, if you are on a compact manifold and you run the Ricci flow, the flow becomes spherical. And that gives another, the flow proof of the uniformization theorem, at least in the compact case. But somehow in their proof, they used at some point the uniformization theorem. So then there was a paper of Chen, Lu, and Tian where they completely removed it, and now there is the flow proof of the uniformization theorem, at least in the compact case. Okay, so as I said, Richard introduced this flow in the 80s, where he dealt with compact three-dimensional Riemannian manifolds. And he considered there a manifold which has strictly positive Ricci curvature. And what he proved in that paper is the following. So he started running the Ricci flow on that manifold, starting with that metric with the strictly positive Ricci curvature. And by using the flow, he managed to prove that the manifold also admits a metric of constant positive curvature and hence is a quotient of S3. So basically how he did it, again, he reparametrized the flow and proved that then it exponentially converges as time approaches to infinity to a round sphere. And so in his proof there, he used the tensorial maximum principle, because you see his condition initially was the positive Ricci curvature. And he proved that that is preserved along the flow, at least in 3 dimensions, right? So he proved it by using this tensorial maximum principle. And then he also came up with this very nice quantity, which I wrote in blue. You can see it's the norm of the Ricci squared minus 1/3 of scalar curvature squared. And you can write that in terms of the eigenvalues of the Ricci, like I did in this blue equation, right? And then what he did, actually, he proved the maximum principle, which involves this quantity, which tells you somehow how these eigenvalues get pinched to each other as you approach the singular time, basically. So what he considered was this quantity F, which is in red, which is Ricci squared minus 1/3 R squared over R to the 2 minus delta for some delta bigger than 0. So this quantity F is the one which breaks the scaling invariance. So if delta were 0, this quantity would be scaling invariant. But since you have this delta bigger than 0, it breaks the scaling invariance. And he considered the evolution of F along the flow, and he proved that this is uniformly bounded along the flow, which means that once you rescale, right? Because the flow will encounter the finite time singularity. So, but you rescale and then you let time go to plus infinity. So you will get that then this quantity goes to zero, basically, right? So that these curvatures get pinched to each other once you rescale the flow. That's how you will see the convergence to the round sphere, basically. Right, so what is important here to notice that at a finite singular time, the scalar curvature actually goes to infinity, right? So that's why like this delta helps you here, right? So because once you rescale and you consider when the rescale time goes to infinity, which corresponds to the unrescaled time going to the singular time, you will exactly get zero on the right-hand side. Then in a more recent work, which was, that was all before Perelman's work. After Perelman's work, there was like a nice result of Brendle and Shen, who also used the Ricci flow for manifolds with quarter-pinch sectional curvatures. So, and we will say that a manifold has a 0.5 quarter-pinch sectional curvature if it has, first of all, positive sectional curvature and the ratio of the maximum and the minimum sectional curvature at that point is less than 4. And they proved that if M is compact and N is greater or equal than 4 with this condition, then M admits a metric of constant curvature and therefore is diffeomorphic to the spherical space form. Right? So, like in order to prove that, they again use the Ricci flow in a similar manner, like where Hamilton used the Ricci flow in the case of 3D manifolds. And Bohm and Wilking also proved similar result, assuming that the full curvature operator is positive. So like in between these two works, there was like, of course, like ingenious work of Perelman, whose one of big observations was that the Ricci flow is the gradient flow of a certain functional, which is called nowadays the Perelman's functional. And that helped him finish the Hamilton's program to prove the Poincaré conjecture. One of the big consequences of this Perelman's functional, which appeared to be monotone also along the flow, is that he managed to prove the volume non-collapsing theorem, which was somehow lacking in original Hamilton's work. And that was a big breakthrough and enabled him to also carry out the whole program. So, like, I will just briefly say that Hamilton's program for proving this conjecture is like to put an arbitrary metric on an arbitrary simply connected tree manifold and then evolve it by the Ricci flow. And then what you expect is that Ricci flow improves the properties of that initial metric along the flow, like what we saw, like in the case of when you assume that the manifold has allows a metric of positive Ricci curvature, then we saw that the flow actually converges to a metric of constant sectional curvature, right? So you expect that the Ricci flow, because it's a nice parabolic equation, improves the properties of the metric along the flow, and that you will be able to say something about the topology of your initial manifold. So that was the main idea. And the Ricci flow in 3 dimensions and higher is not that easy as in dimension 2, because the singularities, even more complicated singularities, occur after a finite time. And what Perelman did is how he showed how to deal with those singularities, how to continue the flow past these singularities using something which is called a surgery, right? So he runs the flow then until so what does it mean first that he runs into the singularity? I wrote it also in this slide that capital T is called the singular time if the maximum of the norm of the Riemannian curvature is going up, so goes to infinity. And then I also managed to show that basically at the singular time, if the capital T is a finite singular time, then actually the norm of the Ricci curvature has to blow up, because otherwise, if it stays uniformly bounded, you can prove that you can continue smoothly flow past this time capital T, right? So this is how you characterize the singular time in the Ricci flow. And what Perelman showed is like, by using also Hamilton's ideas, is that when you encounter these places in the manifold where the curvature becomes very large, so namely you are approaching this singularity, then you cut the manifold in several pieces, keeping the track of those pieces that you cut, and then you continue the flow on each of those pieces. And this is called the Ricci flow with surgery. So that's what was used in Perelman's work also to prove the conjecture. So now we know that at the first singular time, or actually at the singular time, we know that the norm of the Riemannian curvature has to blow up by the result of Hamilton. I proved that actually the norm of the Ricci curvature has to blow up. So the question is, and that's still an open problem, does the scalar curvature has to become unbounded at the singular time, capital T? And maybe like that's still an open question. It's pretty hard. There are some partial results in that direction, but like in order to tackle a question like that, you may exploit the evolution of the scalar curvature, which I wrote on this slide. You see that ddt of R, where R is the scalar curvature, is Laplacian of R plus 2 Ricci squared. And now, like when you try to do anything with this equation, of course, the problem is that the full Ricci curvature enters in the equation, and you have no information on the Ricci curvature. So that is like a problem. So the way how you study so now we characterized the singularities. We know what happens at the finite singular time. The way how you study those singularities is usually through a blob procedure. And for those who are not familiar with that, I wrote what that means. So let's take the sequence of times ti going to the singular time, capital T. And then let's consider this quantity qi, which is basically the maximum of the norm of the Riemannian curvature. And then you perform the parabolic rescaling of your metric around this pi ti, right? So you rescale in such a way that this, what I call G tilde sub I, is still a solution to the Ricci flow equation, right? And you have to multiply the metric G by Qi, and you also have to change the time, right? So we introduced this new time as and shift it by Ti. So you see how we do the rescaling. And then like this limit of these rescalings as I approaches to infinity, which we call G infinity tilde of S, is also a Ricci flow solution. And you can see that now it exists for all times from negative infinity up to some time A. And this is what we call the singularity model. And in order to understand the singularities, you want to understand those singularity models. And these are also called the ancient solutions. So why? Because they come all the way from negative infinity, from time negative infinity. And in order to understand those singularities, your ultimate goal would be to classify those singularity models, which is a very hard question, as you will see. So like when we talk about the singularities, we will distinguish between two types of singularities. So there is something which is called type 1, and there is something which is called the type 2 singularity. So let's assume that capital T is a singular time. And then you will say that the Ricci flow develops a type 1 singularity if you take the maximum of the Riemannian curvature, you multiply it by this time to blow up, and you look at the limb sup as little t approaches to capital T. If that quantity is bounded, then you say that you have like a type 1 singularities, and they are usually better behaved and easier to control. If you don't have such a condition, then you say that you have a type 2 singularity. So where does this capital T minus T basically appear from? So if you take this the norm of the Riemannian curvature, you write the evolution equation, and just by a very simple maximum principle, you can prove that if capital T is the singular time, so what do we know about the singular time? We know that the norm of the Riemannian curvature becomes infinity at capital T. If you use that, then you can actually prove that the supremum of the norm of the Riemannian curvature has to be greater than 1/8 times capital T minus T. So it cannot blow up at a slower rate than that. Okay, it can be just like faster than that. Okay, so but if it blows up at this rate, capital T minus T, then we call it type 1 singularity. And so as I already said, I already defined these ancient solutions, and these are solutions that exist from negative infinity up to some time A. And if this A is less than infinity, we just call them ancient solutions. And if A is equal to infinity, then we call them eternal solutions. And the ancient solutions usually occur as singularity models of type 1 singularities, and eternal solutions they arise as blow-up limits of type 2 singularities. So I'll just bring up this slide. So you see, like, once again, ancient solutions are those that exist from negative infinity to some a, where we allow, there is a typo here, this S should be an a, is in 0 to infinity. And if it's equal to infinity, we call them eternal solutions. So just like emphasizing that, because we will need this terminology also later. Okay, so examples. The simplest examples of these ancient solutions are the solitons, right? So the solitons are the solutions to the Ricci flow, right, that solve the equation, and they just move along the flow by diffeomorphisms and homotheties, right? So somehow, if you know the solution at one time slice, you can recover it at all time slices, right? Because it just changes by diffeomorphisms and homotheties. And as you will see, they very often model finite time singularities, and these Ricci solitons we can view also as generalization of Einstein metrics, which we are all familiar with. And I'm going to define the gradient Ricci soliton for you. Again, that's a Ricci flow solution for which there exists this potential function f, so that this equation is also satisfied. Rij plus the Hessian of f is rho gij. And if rho is equal to 0, then this is just called the steady soliton, in which case the solution just moves by diffeomorphisms. And if rho is different from 0, then you also have to include the homotheties. And you will distinguish between the cases where rho is positive, in which case you have a shrinking soliton, which shrinks at some and becomes singular at some finite time, capital T. And then you have expanding, which exists all the way up to time plus infinity. Right? They're just expanding. And some, let's say, like typical examples of solitons to the Ricci flow equation, like also to other geometric PDEs, are like the spheres, you see, which are the shrinking solitons. They just shrink in finite time until they become extinct. Then we have the cylinders, which also shrink. And like if you go up to time negative infinity, they just become bigger and bigger and thicker and thicker. And if you go to some finite time, they just shrink to a line, right? They collapse to a line. So that's how they behave along the flow. And then, I also mentioned the steady solitons. I drew like a typical picture that you should have in mind when we talk about the steady solitons that just move by diffeomorphisms, right? Okay, but of course, like the picture is not so simple, because besides from these like solitons, which only move by diffeomorphisms and homotheties, there are also other ancient or eternal or ancient solutions which are not the solitons, right? So you don't have this extra formula for them. By extra formula, I mean the one that we had on the previous slide. So this one here, right? Because all solitons are the solutions to the Ricci flow and plus satisfy this nice elliptic PDE. Okay, so and these objects which are like ancient solutions but not the solitons, what you can have in mind is the picture that I drew at the end of the slide. Usually, like let's say in the compact case, you can view them as two. So let's say these steady solitons which are glued together by something in between, which resembles more and more like a cylinder as the time approaches to negative infinity, so that you make your picture, let's say, compact, right? So, I mean, there are solutions that look like that. And solitons, as I said, often appear as singularity models, but of course not all the time. And Richard Hamilton introduced a technique in which he characterizes the steady solitons, actually where he classifies the eternal solutions to geometric flows which have no negative curvature operator and attain a space-time scalar curvature at the maximum. And he proves that under these conditions, this eternal solution, which again, remember, is just a solution to the Ricci flow that exists from negative infinity to plus infinity. And in this paper, he actually proves that it has to be a steady soliton. Right? And we also know that these eternal solutions appear as blow-up limits when you study type 2 singularities. If you carefully choose the sequence of points around which you will blow up, then you develop these eternal solutions as type 2 singularity models. And you can always perform this blow-up limit to satisfy the condition that the scalar, if you have the right curvature conditions, that like the scalar curvature attains its space-time maximum. And under suitably, of course, curvature conditions for your flow, you can guarantee that the limit has no negative curvature operator, in which case you know that the singularity model has to be a steady soliton. So the classification of singularity models in that case boils down to the classification of steady solitons, which is somewhat easier. And Hamilton's technique in this paper relies on the maximum principle and some Harnack inequalities. He also proves for the Ricci flow. As I said, type 1 singularities are easier to understand. And I'm going to remind you that type 1 singularities are the ones which do not blow up worse than a constant over time to blow up, right? And in a paper by Neighbor, Busano, and these are two papers. One was by Neighbor, and the other one was by Busano, Anderson, Topping. They show that, if you let's say that your flow is type 1, you can have only type 1 singularities. Then they show that if I take any lambda j going to plus infinity and I parabolically rescale the flow, so I consider this sequence of solutions Gj, which is lambda j times g of t plus little t, lambda j to -1, as j approaches to infinity, they prove that this always converges to a non-trivial gradient shrinking Ricci soliton. Here, non-trivial means that it's non-flat, right? Because if you converge to something, of course, flat, then you have no information about the singularity. But they prove that it has to be non-trivial in the case you encounter the singularity, which means that in the case of the type 1 flow, right, the singularity models are given by this gradient shrinking Ricci solitons. So classifying singularity models in this case boils down to classifying these shrinking Ricci solitons. Okay, but let's now discuss also the cases where you don't have only the solitons. So I'm going to start with the case of 2D, okay, where we saw that the equation just becomes a scalar equation because, like the Ricci, you can write as 1/2 the scalar curvature times the metric. And like in 2D, the Ricci flow also preserves the conformal class. So you can just write everything, as we will see on the next slide, in terms of the scalar equation for this conformal factor. And we already know, as I mentioned earlier, by the result of Hamilton and Chow, that if we are considering the compact case, that after renormalization, the Ricci flow will exponentially converge to a sphere. Right? So hence, we can choose this parametrization on which is just a global parametrization on a sphere of a round spherical metric, and I can then write the solution to my flow as G is equal to U times this limiting metric GS2, right? So the Ricci flow equation in this case, but this holds only in dimension 2, is equivalent to the evolution equation of this conformal factor U. So instead of studying the Ricci flow equation, you, in this case, you can just study this logarithmic porous medium equation, which I wrote, that U sub t is the Laplacian of log of U minus 2, where the Laplacian is with respect to the round metric on S2. And analyzing the ancient solutions in this case to the Ricci flow is analyzing the ancient solutions just to this PDE. And we have also the candidates for those solutions. Of course, you have always the round sphere, which we know that it is an ancient solution. But there is also this other one, which is called the King-Rosenau solution, which is given actually in a very explicit form. You can even write what these A of t and B of t are. This King-Rosenau solution looks like two steady solitons. Like if you remember the picture I had earlier, we have, I had two steady solitons, and I said you connect them with something in between. right? So to make the picture like looks compact, so it looks more or less like an oval, right? And like these are the solutions which are not solitons, and like but are still ancient. And some time ago we proved with the Scalopoulos and Hamilton that the only ancient solutions to the Ricci flow on S2 are the contracting spheres and these King-Rosenov solutions. So you can completely classify them, right? And this is the theorem in the compact case. In the non-compact case, right, again in 2D, we know that these ancient solutions, which have at least bounded curvature at each time slice, because now I'm not assuming compactness, right? But like I have to assume that at each time slice, my curvature is bounded uniformly in space. We know that like every 2D non-compact ancient solution has to be actually eternal. It exists from negative infinity to plus infinity. And then there was a paper of Daskalopoulos and myself, and then another paper by Ben Chow's student, Chu. And if you combine these two results, you can actually get that the only non-flat, non-compact ancient solutions to the Ricci flow, where you assume, again, the bounded curvature, right, at each time slice, not uniformly in time, but just at each time slice, is the cigar soliton. And what is the cigar soliton? It is, again, a complete, non-compact, steady soliton on R2, which was discovered by Richard Hamilton, and you can write that like metric very explicitly, like I wrote on this slide. And we will keep in mind also that cigar solitons and the King-Rosenov solutions are both collapsed in terms of Perelman's definition of non-collapsing, which also for some of you who are not familiar, I wrote the definition that if we have Mg, we will call it kappa non-collapsed if for every this ball of radius R, where we can control the Riemannian curvature by 1 over R squared in that ball, the volume of the ball is bounded from below by kappa R to the n. And by using like that functional, which is monotone along the flow, Perelman shows that this condition is actually preserved along the flow, which was a big breakthrough. What about the ancient solutions in 3 dimensions, right? What can we say there? Well, I mean, even in 3 dimensions, the situation is already much more complicated, because if you like allow, let's say, collapsing, then there are like solutions that are collapsed, and they were constructed. Many solutions that are, let's say, collapsed. They were constructed by Fateyev, and in the compact case. And then Gilai actually very recently constructed also collapsed 3D solutions in the non-compact case. And these are solutions that at infinity behave like R cross a cigar, right? And I already told you that cigar is collapsed, right? So if you attempt to do any kind of classification in 3D, then you should at least focus on the examples which are kappa non-collapsed. And Perelman showed that kappa non-collapsed condition is preserved along the flow. So when you study the singularities of the flow, you will know that the singularity model is also kappa non-collapsed. So it makes sense to actually consider like these singularity models, which are ancient solutions and which are kappa non-collapsed. Because like if they come as blow-up limits around the singularity of the flow, they have to be kappa non-collapsed. Yeah. Okay, and like so here, like I'm not going to go detailed in this description here, which we have on the slide, because we are running out of time. But I will just say that like the analogous solution to the King-Rosenov.
You have 20 minutes because you started 10 minutes late.
Oh, I have 20 minutes. Oh, okay. Then maybe I can just tell you about these Perelman solutions, right? Which are the analogs of the King-Rosenov solutions, right? So these solutions are not the solitons, they are ancient solutions to the Ricci flow, and they are rotationally symmetric. And the way how he constructed them is just, so I will just say a few words then. So he takes any L, right? L is just a positive number bigger than 1, and he considers this rotationally symmetric metric, which I call G sub L, at time 0, right? And then, like, so this, like, he just takes something which metrically looks like a round sphere cross this negative LL, which is part of a cylinder, and then he caps it off. Sorry? And he caps it off like smoothly by these two caps, right, to make his manifold compact. That is his initial data. Then he runs the flow. He then has this family of solutions, G sub L of t. He would like to take the limit as L approaches to infinity. But first, he has to be a little bit careful how will he take the limit, because he would like to say, okay, when I take the limit as L approaches to infinity, I'm going to converge to an ancient solution, which is not a sphere, right? So we have to be a little bit careful how we take this limit. So the first thing that he shows is that actually Perelman doesn't show it. He just claims that that's the solution, but then other people did work to show all these things, that each of these metrics GL becomes singular time capital T sub L. So first they prove that this time is uniformly bounded from above and below independently of L. And then they choose another time, this little T sub L, at which the oscillation of the sectional curvatures of metric G sub L at time little t sub L is 1 plus delta for some delta bigger than 0. Okay, which you can prove it exists. And then they do this rescaling like I did at the end of the slide, right? So you do this parabolic rescaling, and then you have to argue that you indeed can take the limit of these rescaled solutions as L approaches to infinity, and that you will converge to something which is ancient, first of all. And because of this condition here, because of the choice of this little t sub L, right? Because of the choice of this little t sub L, which corresponds to this new time, t is equal to -1, basically, you can guarantee that what you get in the limit will still satisfy this condition, that at some time the oscillation of these sectional curvatures will be 1 plus delta for delta bigger than 0. So hence you will not have a sphere, but you will have a new solution indeed. And there is no explicit formula for that solution. We know it is rotationally symmetric, that it has positive curvature. And we can just say something about the asymptotics of that solution, namely, it's compact. And now take any sequence of points in your manifold and any sequence of times ti going to negative infinity, right? So let's call them pi, ti, and rescale, do the parabolic rescaling around those points by the scalar curvature at those points, right? So you can take the limit, you can argue you can take the limit, and this limit is always either around cylinder S2 cross R or the Bryant soliton. Bryant soliton is a steady soliton to the Ricci flow, which is non-compact and moves only by diffeomorphisms. I'm going to say just a few words about it on the next slide. But this is how this Perelman solution looks like. So you can, you know that, but there is no any formula for it. And there is an analog of that solution also in higher dimensions, right? So this is called now the Perelman's solution. So now I want to list here the examples that we know so far of three-dimensional non-collapsed ancient Ricci flow solutions. Right? So we know we have a round cylinder, which is non-compact, and it is a gradient shrinking Ricci soliton, satisfying also this nice elliptic equation. Then we have also the round sphere, okay, which we already discussed. We have Perelman solution, which I just showed you how it has been constructed. And we know it's not a soliton, unlike all the others. And it's not given in the closed form, unlike King-Rosenau solution in 2D. And then the fourth candidate that we have is the Bryant soliton, which is non-compact, non-collapsed. And right, it is steady Ricci soliton, which means that it moves only by diffeomorphisms and satisfies this nice elliptic equation, right? And the Hessian of f is Rij. So it just moves by diffeomorphisms, which are generated by the gradient of f. Okay, so we have these four candidates. Our goal is to prove that these are the only examples, that you have nothing else in 3D, right? So that would be the ideal picture. And that's what Perelman actually suggested in his first paper. So I'm just going to tell you here the Bryant soliton was constructed by Robert Bryant, and he proved that it's a unique, complete, non-flat, steady, rotationally symmetric soliton in 3D. We know it has positive sectional curvature. The maximum is at the center of rotation. And then if I write this metric, since I know it's the rotationally symmetric, if I choose this parametrization to write the metric, I can just get this PDE for Z, which describes the Bryant soliton. And Brandle more recently actually proved that it's not only unique among rotationally symmetric steady Ricci solitons, but it's unique among all non-collapsed steady Ricci solitons in dimension 3. So the way how he proves it that it has to be rotationally symmetric and hence is unique by the result of Robert Bryant. Right. So, okay. So like you just keep in mind that our goal somehow by the end of the talk is to actually say that these four are the only candidates for these three-dimensional non-compact ancient Ricci flow solutions. Okay, so I'm going to now define something what Perelman defines in his paper and calls them ancient kappa solutions. So these are complete kappa non-collapsed ancient solutions which have bounded and non-negative curvature. And he proves that in 3 dimensions, when you study the finite time singularities, right, they are always modeled on these ancient kappa solutions, right? So you don't need to assume anything on your initial 3D manifold. You always know that the singularity model of the Ricci flow will be modeled on these kappa solutions. So why is that? So I will just briefly say, because in 3D is also very special because you have, first of all, Hamilton-Ivy pinching estimate. And this Hamilton-Ivy pinching estimate in 3D will actually make sure that like you can use it actually to prove that if you have an ancient solution, it always has no negative sectional curvature, first of all. And once you have that, you have like Harnack estimate that was proved by Richard Hamilton, and which has also as a consequence that for ancient solutions, like this scalar curvature actually increases in time pointwise, which means that like the scalar curvature is uniformly bounded as you go like all the way up to time negative infinity. But since you have positivity condition, then the full curvature is actually controlled by the scalar curvature. So you have also the boundness of the curvature, right? So that is why when you study like in 3D singularity models, they are always these ancient kappa solutions. Okay, and Brandle proved that if you have a non-compact 3-dimensional ancient kappa solution, that it has to be either a shrinking cylinder or the Bryant soliton, right? Which covers the 2 complete candidates from our list here. So I'm just going to show you here. So we have like the first one is a round cylinder and the last one was the Bryant soliton. These are the 2 non-compact candidates and the remaining 2 are the compact candidates. And Perelman solution is the only one which is not a soliton. Okay, so as a consequence of his result, you can actually see that the only possible blow-up limits, like in the case of singularities in 3D, are either the round sphere, quotient of a cylinder, or the Bryant soliton. These are the only candidates. So he proves that in his paper. Okay, but like in the paper of Perelman, he also like says that the only possibility for compact solutions is only the spheres or the Perelman solutions, and there is nothing else in between. Okay, so that's what I want to focus a little bit next. So before like I state that, I will just say that like how Brandle actually proves his theorem, right? So he proves it the following way. He considers this 3-dimensional ancient kappa solution, and the first he shows is that it has to be rotationally symmetric. Okay. And then once he proves that it has to be rotationally symmetric, okay, then he shows that it has to be a steady soliton, and hence it is the Bryant soliton. Okay, so that's how he proves it. So first step in the proof is to prove that such a solution has to have rotational symmetry. So now we consider it like the compact 3D kappa solutions, and together with Brandle and Pascalopoulos, like we proved that such solution has to be also rotationally symmetric. What we do in this, to prove this theorem, we somehow adapt Brandle's arguments to our closed case. Okay, so you have to be more careful because you are not complete anymore, you are compact, but you can work out and use his arguments to adapt them to a compact case to prove that you indeed have to be rotationally symmetric even in the compact case. And independently, Baumler and Kleiner proved the same result, but using completely different methods. So they use their notion of singular Ricci flow for that. Okay, so the way how, I'm just going to say to you why you should expect to have something like that is the following. So let's take any 3D, ancient compact non-collapsed solution, right, that we are considering. So the first thing that you can prove is that there exists a sequence of points in the manifold and times ti going to negative infinity, so that when you rescale around them by the scalar curvature, and take the limit will be around the cylinder S2 cross R, right? And this is what we call the asymptotic shrinking soliton, right? Which is somehow buried into your solution, right? Has the so you prove that there exists one sequence with that property, okay? But then as a next step, you show, okay, now I will pick any sequence, xk, tk, where tk approaches to negative infinity. I rescale the flow by the scalar curvature at xk, tk. I take the limit, and then we show that the limit always has to be either the shrinking cylinder or the Bryant soliton. And remember, both of them, the shrinking cylinders and the Bryant solitons, they're both rotationally symmetric. So this means that, if I look at my solution and I go to time negative infinity, no matter how I rescale, I always see something in the limit which is rotationally symmetric, right? So this should indicate maybe that my solution, right, because it's an ancient solution, so should have some rigidity, maybe should also be rotationally symmetric itself. Right, and but these are the main steps that you prove first that indicate that what you are aiming for is correct, and then you do more work to prove that you indeed have rotational symmetry. Once you have rotational symmetry, right, we can write our metric like I wrote on this slide here. Right, so where S is just the distance function to the equator, and then the Ricci flow equation just becomes equivalent to the equation for this radius function psi, right? Where you just keep in mind the ddt and dds do not commute here. So, okay, and then you can also perform this parabolic rescaling, because what happens for your ancient kappa solution is that basically, when you take this sequence of points xk, tk, which are in the middle, you will always converge to a cylinder, right? So therefore, you take this parabolic rescaling, and then you will be able to say that around a fixed point, this u will always converge, let's say, to square root of 2, which corresponds to a round cylinder, right? Okay, so we actually studied this rescaled equation for you. I mean, here I just wrote the equation for psi, and I wrote the parabolic rescaling, so you can just write the corresponding equation for you. And together with Angen and Brendle and Daskalopoulos, we first proved that now if you have any rotationally symmetric compact kappa solution, which is not S3, they all have the same precise matched asymptotics, right? So this theorem is still not about the uniqueness, but we first show that the asymptotics of our solution have to be unique, right? And here I just, on this slide, I just wrote this precise asymptotics in terms of my radius u. And you will see, I will just so we have these three regions here. I'm not going to talk about all of them. I'm just going to say that the parabolic region is the one which is actually the cylindrical region where your solution resembles to a cylinder. U is equal to square root of 2, is just the equation of a cylinder. And then you have this other term, sigma squared minus 2 over 8 tau, which is the second order asymptotics. Right? And this term sigma squared minus 2 is exactly the eigenvector of the linearized equation of the Ricci flow around the cylinder corresponding to the zero eigenvalue. Right? So this just tells you that the zero eigenvalue of your linearized operator, or the zero mode of your linearized operator around the cylinder of the Ricci flow, is the dominating one. Okay, so this is what we show. And then I'm just gonna, intermediate region is something that connects this cylindrical and the tip region. And I'm just gonna say in the tip region, we also proved that after appropriate rescaling, your rescaled solutions converge to the Bryant soliton. Right? So all so this was the first theorem that, like, if I consider any 3D kappa solution, it has to have these asymptotics, right? No matter what I take. Now, by using this uniqueness of asymptotics and the fact that we know now that our solution is rotationally symmetric, we can show the following theorem, which we did together with Brendle and Daskalopoulos a little later. So if S3G of T is a compact kappa solution to the Ricci flow, it has to be either S3 or the Perelman's solution. Right? So we indeed verify, like Perelman's conjecture, that you can have like only those 4 candidates as ancient kappa solutions. What about higher dimensions, right? Can we expect similar classification of ancient solutions in higher dimensions? Well, then the situation becomes even more complicated, because Backus, Kong, and Ni, they construct many like examples which are positively curved in higher dimensions, which are both collapsed and non-collapsed also. Like it was also, there was a speculation that any kappa solutions on spheres in higher dimensions has to be rotationally symmetric, but that was also refuted by one of the examples of Backus, Kong, and Ni. So this means that even if you just assume like some natural condition, let's say positive curvature operator, that is essentially not enough to do any kind of classification that we did in the 3D case. Okay, so maybe what could be like the maybe you could prove the analog of our theorem that we have in 3D, also in higher dimensions. But if you maybe assume that asymptotic soliton is a round cylinder, S n minus 1 cross R, right? Because you can have all these generalized cylinders, which like in higher dimensions, which complicate the whole thing. But let's say that you assume that you converge to the round cylinder Sn minus 1 cross R, that you asymptotically look like that. So then maybe you can be in some good shape to accomplish the similar classification. Okay, so we haven't done that so far in higher dimensions, but we did consider higher dimensions more recently in together with Brendle, Daskalopoulos, and Naf, but where we actually focused on some other curvature conditions, which is the positive isotropic curvature. And then under those conditions, we actually managed to show that many properties that we have in 3D case also persists. And then we could also say that we have the same kind of classification as in 3D. First, Brendle and Naf did it in the complete case, and then all of us we did it in the compact case, right? So we just had all the techniques already developed. We just had to kind of, adapt them to like a higher dimensional case. Okay, so thank you for your attention.